Welcome to DB Workshop channel. Today we will discuss few concepts about virtual memory. Let's start. We will discuss these topics. First of all, what is paging? Paging is just dividing the part of the memory into a fixed partitions of the same size with respect to the process in question. For example, if you have some process, so we have to decide that how many pages are there in that process. For example, if we have 3 pages in that process, so we just create a page table and we have 3 page entries for that process like P1, P2, P3. So for each entry in a page table will be pointing to the frame, and those frames will be there in main memory. So their technique is called paging. This is contiguous memory allocation. That means memory will be ordered, allocated sequentially. Segmentation is another technique in where we have a process and we just take the process, and for that process we have to decide that how many modules there in a process. So it may not be in equal in size. For example, depends upon the module there in a process. We may have a 3-4 modules. Some modules will be bigger and some modules will be smaller. So based upon those module sizes we create segment table, and that segment table will have pointers to the actual main memory. So this technique is called segmentation. Okay, internal fragmentation. For example, if we have a process P1 and we have a page table for that process, and this process contains 5 frames, so these are the page table entries and these are the frame numbers. For example, it contains 5 frames, so every frame number will be have a pointer to the main memory, and that will point to the frames. So for example, the first frame F1 is allocated and there is some space wasted after that, and F2 is also allocated, and there will also be in this partition there will be some of the space will be left over here. That will be a wastage of space. So whatever is left over for that particular from that particular frame or partition is called internal fragmentation. That means if you have a partition of 100 KB and you have just allocated 80 KB, so just a 20 KB, whatever is left over is called internal fragmentation. Next, external fragmentation. In the same example, if we say that after some time some of the allocated pages move out, that means those pages are emptied out. So these space will be free for the allocation, but because this is not contiguous, so we cannot use it. That's why this is called external fragmentation. If we want to share the memory, for example, this is off topic, but the shared memory uses mutual exclusion. That is a critical section concept. That means to prevent a race condition. For example, if 2 processes want to share the same main memory partition, so they require mutual exclusion principle. This is how the same main memory location can be shared across the processes. Next one, static partition of memory or fixed partition of memory. Because there are 2 memory management techniques like contiguous, that means sequentially ordered allocation of the memory, and non-contiguous, we could just allocate the memory in a random order. So in contiguous technique we have 2 kind of techniques. One is a fixed, that means a static or fixed partition. Variable, that means a dynamic partition. So the problem with the static partition, that means space allocation is not that optimal. Some space will be wasted. One solution is over the system memory allocation. So what is system? Is just a memory allocation technique where we have just divide the, it is all about how we create the partition of the memory. So we just divide it in the powers of 2. It is easy to implement, and we could allocate the blocks in a correct size. It is easy to merge the adjacent holes. Holes means whatever is memory moves out of the memory, that emptied out space is called hole, and it is easy to merge the adjacent holes. If we have a memory allocation in the powers of 2, we call it what is system memory allocation. This is a kernel level memory allocation. Disadvantage, that means we have to allocate in the powers of 2, so that means sometimes it may lead to the internal fragmentation. For example, if I have to allocate the 30 MB, but I have 30 MB, but in the 2's power of 2 I can only create a partition of 32 MB, so 2 MB is wasted over there, so that is called internal fragmentation. So this is just a example. Buddy system is a older kernel memory allocation algorithm where we just allocate the memory in the powers of 2. For example, if we have a physical address space of 128 KB and we want to allocate a 18 KB process in that physical address space, how we do that? What would be the size of the partition? Because 18 KB process have to allocated, so if I keep on dividing the memory in the powers of 2, I could just create a 2 partition of 64 KB. Further dividing it, I can create a partition of 32 KB. I can go further and create a partition of 62 KB. Wait a minute, I cannot create a 16 KB partition because my process is of 18 KB size, so I have to stop over here and I have to just create a partition up to 32 KB. So 18 KB can fit any one of those partitions. Virtual memory, a storage scheme where we use address translation concept. That means virtual memory is something that is just appear to present, it is not actually present, so it is just to provide illusion that you have a very big memory, but it is not there. It use this secondary memory as a appears to be as a main memory. So how it does that? It does not load the full complete process in a single go. It just load the different part of the process into the main memory, but the user thinks that all the parts of his process in the main memory, but it just a swap in and swap out. So what is the benefit of it? Benefit is you don't have to purchase a more RAM. You can just run the bigger processes when you have a small RAM, and it just increase the degree of multi-programming. That means many processes can run concurrently, parallelly, but the problem is CPU utilization increased because you have to swap in, swap out the pages or segments. Advantage of the virtual memory, you need a less RAM and you don't need to purchase more RAM for that. And plus point is you have a multi-programming, multiple processes can run at the same time when you have a smaller RAM. Disadvantage, system gets slow, CPU is used more, you have to swap in and swap out the processes, so that kind of overhead and work has to be done behind the scene. Demand paging is a popular method in a virtual memory. That means only those pages will be loaded which are being used. Those pages which are not being used is just put on the secondary memory, and it is just to use the least recently method LRU. It use LRU. Those pages which are not demanded, not being used, is not being loaded. If page is not there, if it is trying to load some page, trying to access some page and page is not there, it is just a page fault will occur, and that page is being loaded from the secondary memory to the main memory. And there are various kind of the page replacement algorithm which replace the pages. We will study it in the later slides. We can use TLB. We will discuss TLB also. TLB means translation look aside buffer. It uses a memory cache. It is done at the hardware level. Less time is taken by CPU to use the TLB instead of main memory. It just use this cache at the hardware level. It just CPU can fastly access this TLB Lookaside translation Lookaside buffer because it is smaller than main memory, so that it can be accessed faster. It is, on the other hand, it is cheaper than registered. However, it is bigger than registers, so that it can store more, but it is smaller than main memory, so it is fast. Instead of going to the main memory, it is a kind of caching. It uses the concept of locality of reference. It only contains those pages which are used recently or frequently. Locality of reference, what we mean by it. Principle of locality, that means the CPU can access the same set of the memory location again and again, quickly, repeatedly. The same set of data it can access. Temporal locality of reference, it is again talking about a memory access location. When CPU wants to access the memory location, maybe data or resource again and again within short span of time. For example, if something is being accessed again and again, and there is a probability that it will be accessed again and again, so there we use the concept of temporal locality. So those pages, or those, for example, if you're talking about a maybe COA, I mean computer organization and architecture where we study. For example, if you want to pull some some data from the hard disk or from the main memory, it just it won't access that particular byte. It just load the complete block. So that means it just bring those blocks also, those data also, which is not being required, but later on there is a probability that that is being used later on. Lookaside buffer, that means most recently used pages, addresses, translation will be present in it because there is a high probability that they are going to be used again in future. So this is called temporal locality. Spatial locality of reference, this means again this is the principle of locality. CPU accesses the same set of the memory location again and again within the closed storage location. So look ahead buffer, for example, a look ahead compiler where we know that one or more symbol forward from the position where we currently in. So where we are, the compiler is just load the symbols forward from the position where it is currently in. That is, it scan the nearby area also, so that later on when that is being required, it would have already there in memory. Like in computer organization and architecture, similar thing happen. For example, when we refer to a data or some address, a block of nearby data or a complete block is just loaded into the memory. It is again called spatial locality. Sequentially locality of reference, which means it is a special case of the spatial locality. For example, CPU access the same set of the locations again and again. For example, if you have access the sequentially stored the data structure, for example, if you have a one-dimensional array and if you want to access those locations in a single go, it is just pull all those information in a single go and put it in TLB. It is called sequentially locality of reference, TLB. For example, if I have to access a big tables and my block size is 8K, and if you want to I can retrieve all the blocks in a single go or multi-block read kind of thing. You can access that complete data structure that is stored sequentially, so that we can traverse, for example, we can traverse a one-dimensional array, and it is just load every information that is sequentially stored into the TLB, so that the next time we require those blocks or data, we can access it quickly from the TLB instead of going to the main memory. Virtual memory, it allows the programs to run which require more memory than the actual main memory size. Thrashing, if the processor frequently access the page that is not there in memory, internet will just trigger the page fault, and page fault is something that it is just trying to access the page which is not there in the memory. So what it will do, it will ask to load that memory from the secondary memory and load it into the main memory. So thrashing occurs when the processes on the system require more memory than it has. For example, if you have a very small memory and everything you want to load and everything is there in on the second on the secondary memory, but each and every process will try to go for each of its own pages, and it will just keep on swap in and swap out, and it will keep on every time page fault will occur. So that means lot of page fault will occur, and it is a problem. It will just trigger to the tracing, because there is a limit of the virtual memory. In that case, we have to just increase the RAM, because there is just a limit of using the virtual memory. Otherwise you just have to face these problems, because your RAM is so less, it will again and again page fault will occur, and everything will be swap in and swap out, and thrashing will occur. So it will just low CPU utilization, and then OS spend most of the time and swap to the disk and uh, load and swap in and swap out. So first of all, we know that what is the swap space. That means used to store the process data. It is just a temporary area where we store the data. Swapping creates a lot of fragments, because a lot of the processes move in and move out. So because again and again, if I am just uh, moving the processes from the secondary memory and load it into the main memory, so it can cause a fragmentation. A lot of fragmentation it can cause, because the processes move in and move out. Validates anomaly, it tells that if you have a more and more page faults, so it is a possibility that if you have a more page fault, and if you increase the number of the frames in FIFO page replacement algorithm, that in turn you will have a increase the page fault. So increasing the number of the frames in FIFO page replacement algorithm is not always a good idea. So Bilad's algorithm talk about it. What is multi-level page table? Multi-level page table means if size of the page table is huge, so we could have a multi-level of the page table, so that it can be manageable, and it would be more beneficial. For example, if you have a huge page table, so it is good idea to have a multi-level of the page tables, first level page table, and it will refer to the second level page table, and that will refer to the third level page table, and so on. And then the last level page table will actually refer to the main memory. What is a dirty bit? Sometimes we have we have to keep the track of whether the page in the cache is modified or not. If it is modified, we have to just uh, flag this dirty bit on or off, because modified page sometimes need to copy back into the main memory. So it is just save this to just unnecessary writes on a paging device. For example, we have to study about the external fragmentation. So to solve the external fragmentation, there is a technique called compaction. Compaction means because your data is in a contiguous memory allocation techniques, and a lot of processes move in and move out, and there is a lot of free processes, but the size of those free area is very small. If you want to club that free area and try to club those empty space out, and club it together so that it can be used for the processes, and it can be used efficiently. For example, if you have a chunks of data, for example 2 MB, 3 MB, 4 MB, 5 MB, and your process require 8 MB, so you can have this process compaction technique that can club these empty out chunks so that it can create a uh, big area. For example, if I add 1 MB, 2 MB, 3 MB, and 4 MB chunks, so that I can allocate the 8 MB process, because I can rearrange the data, allocated and unallocated data. How it is possible? It is about to combine the empty space chunks together, but the problem is it's lot of CPU. It is a continuous process. On each process allocation, compaction has to run. It is not an easy process. If the relocation is a static, it is done at the assembly or the load time. What if it is at the dynamic? It has to run at the execution time, and system efficiency goes down because it requires a lot of CPU, and everything CPU is doing has to halt for microseconds, and then it's just to do the translation of those partitions so that it can club the allocated and unallocated space. TLB. TLB contains the keys and tags. It speed up the memory access. It helps when the CPU access the main memory. CPU can access the main memory directly. If the keys and tags found in TLB, it is called TLB hit, and those keys and tags can be directly accessed without going to the page table. But if these keys or tags are not there in TLB, it is called TLB miss. So then CPU has to go again to the page table, and then from the page table it just look out the page table entry, and it has to look out for the frame number, and it will access the actual frame in the main memory. So it is just a long route, and otherwise if it is a TLB hit, it can directly go to that main memory location and access the block or the data it required. So sometimes if there is some process is running, sometimes it would be TLB miss, sometimes it would be TLB miss. So on overall, how we know that how much access time is there? So on overall, we have a formula over here. Effective access time, uh, it is called effective access time. How we calculate it? For example, TLB hit rate. I mean, what is the rate, at what rate it can, there is a probability that it can hit. So for example, hit rate will be directly into the time of access TLB. For example, if I am accessing the TLB, so there is some cost to access the TLB itself also. So, and what is the hit rate? We have to multiply it, because hit rate is 10%, uh, and if I'm taking the 1 nanoseconds to access the TLB, so that means 10% of uh, for cost of the 1 TLB access is 1 nanosecond, so I have to multiply it. Otherwise, because I have to go to the TLB, then I have to go to the main memory also. So for the hit rate, I have to do the two things. First of all, I go to the TLB, I just note down the tag and the key, and then I directly go to the main memory and access the block. So that means two things I am doing. So I will calculate the cost of it, and I will add it together. If it is a miss, then what will happen? It has to go to the TLB, but it is a miss, so that means it has to come back to the main memory, and from the main memory it has to go again. So I have to access the main memory twice, so that means TLB miss rate will be divided by main memory twice. But the second one, the last line, it is just multiplied by the k level paging, because remember we talk about the page table. If I have a two level page table, so it will go to the first page table, then second page table, and then third page table. Or maybe if it is a two level page tables, and first page table, and then main memory, so that means k level paging means if it is a single level, k is a 1. If it is a two level, k is a 2. So that means the number of the levels we have in a page table, that factor will be multiply the cost of accessing, because ultimately we have to reach to the, we are calculating the time, how much time we are investing to reach to the actual data block CPU want to read. So this is the formula for effective access time. Generally we will have some kind of numericals to solve this, and this is very interesting to know this formula. Demand paging is do not is telling us do not load in the memory if it is not actually needed. If it is the first time something is being accessed, some page is being accessed, we have to load it. If it is the first time, it must not, there is a correction over here, it must not be there in the main memory. If it is the first time access, we have to access it from the secondary memory and load it into the main memory. Otherwise, if the same page been accessed again on the second time, it may be in the main memory or it may not be, because page replacement techniques or maybe page fault occur and that may be swap out, so that means move out of the memory, so it may or may not be there. But if it is a first time access, definitely it will not be there in the main memory. If it is a second time access, there is a probability that it is there in the main memory or it may not be there in the main memory, because maybe some other process has just swapped it out on the based on the page replacement algorithm, and so that may be a miss and it may not be there, but it may be there. The thrashing is page fault is too high. CPU is very busy in reading from the secondary memory, and the EAT means effective access time is also very high, so this is a problem. Thrashing means too much of phase fault. CPU wastes too much of time in reading from the second memory, and again all the pages being swapped out because due to the page fault occur due to the other request from the CPU. So this is a problem. In this problem, EAT is high, effective access time is high. Next one, inverted page table. Inverted page table means there is some kind of the global page table that is maintained by operating system for all the processes. The number of entry in inverted page table is equal to the number of the frames in total in the main memory. There is one question over here under paged memory management scheme, simple lock and key memory protection arrangement may be required if fill in the blanks processor do not have address mapping hardware. So answer to it is IO processors, because IO processors will issue the address device controller and there is no translation hardware, then we need to protect the data from being corrupted or changed or written. We have studied these topics in this presentation: virtual memory, cache memory, TLB and thrashing. If you like this video, please subscribe this channel. Please subscribe this channel and support this channel. Thank you very much.